Hi, in this video we'll discuss a representation of digital images in PIL and NumPy, which are two common libraries for image processing in Python. So our learning goals are to understand tensors as multidimensional arrays that we use to represent images, and to gain familiarity with the format of the Python image library images and the NumPy arrays that we use to manipulate images and visualize them with matplotlib. Even though we'll be doing most of the work on the course on PyTorch, it is important to understand the role of both PIL and NumPy as auxiliary libraries for image processing. So something that we should internalize is that what we have in the representation of a pixel is just a level of intensity. So a given pixel on an image, it's a value that has an intensity that's on the range from 0 to 255 when we have a grayscale channel. 0 is used to represent pure black for a pixel on these grayscale levels. 255 is used to represent pure white, and the values in between are a shade of gray. So when we have 8 bits, we can represent this range between 0 and 255. And this is what most consumer displays do. They use 8 bits per channel, and consumer cameras also capture 8 bits per channel. And when I mean channel, it's channel like red, green, and blue. When we have a color image, we're going to have a stack of these intensities. We're going to have an intensity for every channel that we have in the stack. These stacks of images, these stacks of arrays, we call tensors. That's a concept that we're going to see over and over in this course. So this unsigned integer 8 is something that we get when we acquire an image using the storage from disk. When we acquire an image from the JPEG files that are so popular, or from a PNG file that it's also quite popular, you will acquire the image in an intensity between 0 and 255 for every channel that you have, and this is going to be stored in an unsigned integer 8 type because of its efficiency. So when we look at a grayscale image on a screen, we see a familiar shape. In this case, we see the digit 3. However, the computer does not see the digit the same way. Instead, it stores and processes the image as a matrix. So it has no idea about its semantics. It has no understanding of what's the purpose of this set of pixels together. And it is our task as computer vision practitioners to assign meaning and semantics to these stacks of pixels, to teach the computer somehow to learn to recognize patterns, identify objects, and make sense of what appears in these matrices. So here we see an RGB image, and we're describing it as a tensor, a stack of matrices, as I described before. Notice the contrast between our human perception of the satellite image and the computer representation. So this is a beautiful image of this coast, but for the computer it's just a stack of matrices. And if we zoom in this little red area that we have, you will see that we have a stack of 3 matrices, each one of 4 times 4 pixels. Each one has an intensity, and they represent the red, green, and blue channels. So this is something that mimics the biology of what we have in the cone cells in our retinas. We have 3 different types of cone cells. We have short cone cells that detect the blue color. We have medium cone cells that detect green. And then we have long cone cells that detect red. The RGB model mimics this biology. In the digital representation, each channel matches the cone sensitivity, and this is combined to mimic the human color perception. However, human eyes see more colors, and the displays cannot really show the full vision range. The RGB model simplifies the biological complexity that is inherent in our retinas, but it works good enough for most practical purposes. So this slide demonstrates a few basic operations using the Python image library, which is a common tool for opening, inspecting, converting, and saving images in Python. When working with Python and PyTorch, we will commonly use it to open files stored in a JPEG or PNG format. You see here image.open with the path to the image loads an image from your file system. Then it becomes a PIL image object, and we can call methods or attributes on it. When we call the attribute mode, we get as output L for grayscale, we will get RGB for a color image. And when we print size, we'll get 28 times 28, which is the true size of the image in pixels. It's a very, very small image. If I want to see it upscaled, we're going to be using the last statement that you see in this slide. We're going to be using import map.lib.pyplot as PLT, which is going to convert this PIL image into a NumPy array. And this is something that is going to make it appear blown up. And you see here that we also have some utilities to convert from the NumPy array into a PIL image from array. Is something that we can use to convert this NumPy array that you'll see defined in the practical notebook into a PIL image. And something super important is that we can use the functionality of save that we have in the PIL image object to save images after we have done some processing on them. So we can do pil.imageSave and then pass a path to the image, and this would allow us to save this persistently on our disk. So this slide introduces the NumPy n-dimensional array. The n-dimensional array that we have on NumPy is something that we can use to represent grayscale images or color images. ndarray stands for n-dimensional, and this is a tensor. When we stack different matrices together as to represent colors, for example, we have tensors. Here we see a very important usage of the of the NumPy array, which is that we do broadcasting. We take the original values of the stack of the matrix here, and then we take 255 as a value that we subtract from, and this creates a negative of the image. You see now that the background is white, and the digit itself is now drawn in black. Is the opposite of what we had in the previous slide, and we create this with a single line of code. We don't need to loop through the values in the array, because NumPy is performing an operation called broadcasting. It's creating a matrix that has the exact same dimensions as this one under the hood, and then subtracting element-wise by every single value that we have there. And then we can see again the upscale version of this on map.lib. This is why we see this image blown up and not on its real 28 times 28 pixel size. This map.lib library is something that we're going to be using over and over to inspect the results of our training, and also of the images that we have pre-processed before feeding to the neural network. So it's important to gain familiarity with it. Here we see how red, green, and blue images can be produced and manipulated in NumPy. We see that we have a NumPy array that has 3 by 3 pixels, and we are defining here the different intensities in terms of red, green, and blue values on each one of the pixels here. And you can see how do this look. You see how red, green, and blue are represented as this little tensor, and this is the first row of pixels. Then we have the second row where we have a yellow pixel, a magenta pixel, and a cyan pixel, and then we have white, gray, and black pixels. And you see the intensities that correspond to this. I encourage you to play with this little matrix and change intensities. You have this in the practical notebook, and you'll see how combining the different red, green, and blue values produces different colors. And something that is worth looking into and internalizing is how the indexing works in NumPy. We're going to be indexing the values of the array starting on 0 and ending on something that is the length of the dimension minus 1. So if the dimension has 3 elements, the top element that we're going to use to access the content of the array is going to be 2. So 1 minus the dimension, the length of the dimension. So here I'm showing you how we can access the different intensities that we have on the RGB channels, how we can get one of the channels separately and see what is the intensity of the red and green and blue channels as grayscale images. We can also assign some color maps so that we can see the intensity images with red, green, and blue values. This is something that is helpful for interpretability. We can also do this play with the image arithmetic in NumPy that is quite fun. I would recommend you to take a look at this and see how we can select sections inside the NumPy array and assign intensities. And then you see in this example also how we can go back into a PIL image by using the image from array call, and then how we can merge the different images that we have produced into this beautiful square image that we see here with the different colors. You can play with the sections, you can play with the shapes that you're producing with this to gain a bit more familiarity about what we're doing when we do these assignments by index in NumPy. So the last thing that we're going to discuss is the format that we use for NumPy arrays and PIL images to index the channels. So in NumPy we have the dimensions of the tensors specified first with height, then with width, and then with number of channels. And this is something that is different in PIL image tensors. In PIL image tensors, first you have the width, then you have the height, and then you have the attribute mode, which is going to be L for grayscale and RGB for color images. This is something that is good to keep in mind because it's a very common gotcha. So in the next session, we're going to see a bit more of PyTorch and the interplay between NumPy, PIL, and PyTorch, keeping in mind these different standards for height, width, channels, and width, height, and mode. This is important to keep in mind.